we're starting into higher order differential equations. And as always, we'd like to be able to solve problems. I mean, that's why we do math, right? We want to solve problems. And today we're going to say, hey, you know what? There's a nice scenario where we can actually make fantastic progress in solving them. It's a wonderful story. It'll actually take more than just a day, so we're going to be spending probably like a day and a half on it. But first off, we want to do a little bit of cleanup from last time. So let's begin. Now, what did we talk about last time? Well, we talked about these higher order differential equations, and we said, well, what can we say? Well, one nice result is suppose we have the following. Suppose we have a differential equation. So we have an nth derivative plus some function of x times n minus first derivative, so forth, some function of x times just y equals 0. Now, if you remember our terminology from last time, that says, hey, this is nice. It's linear. In other words, we have these nice linear combinations of derivatives of y, and it's also homogeneous. Now, we don't actually need homogeneous to say that there's a solution, but we're going to focus on that case. And so, okay, so that's our differential equation. We also have some initial conditions. And in particular, if you look here, we say we know the value of the function at a point, the value of the derivative of the function at that point, so forth and so on, till we get to n minus first derivative. Now, if you say how many initial conditions are there, well, you actually can tell how many we should have. We have n. That's the key. And it makes sense, right? Because essentially, if we have an nth derivative involved, somehow there are like n integrals involved, and every time you do an integral, there's an extra constant showing up. So we have to have enough information to answer n constants, or put another way, we have n degrees of freedom. So with n pieces of information, that says, aha, these are what the constants need to be so that everything works. Okay, so we have our nice differential equation, we have our initial conditions. And remember, the way we should think about it, initial conditions tell you how to start, differential equation tells you how to move, and so that should determine everything. And that's what happens. So in particular, we have a unique solution. First off, we have a solution, which is good, but there's exactly one. And the solution works for quite a ways. In fact, really, it works as long as these functions that are showing up here are continuous, which oftentimes might be everywhere. So we have quite a nice solution. Okay, so you might say, well, why did we really want to focus on linear and homogeneous? Well, that's sort of the second idea. It says, hey, suppose we have a collection of functions. And these functions are solutions. And again, we say, look, there's not just any number of functions, there's n of them. So there's n functions that we have to our nth order differential equation. And these functions have an additional property, namely that they are linearly independent. Now, recall what's sort of the philosophy behind linearly independent. It says they're essentially different. There's no redundancy. It's not like I say, oh, here's like e to the x, and look, here's e to the x. You're like, what? I already had e to the x. I don't need another one. Give me something new, right? So each one of these functions somehow gives you new things. Okay, so we have a nice set of n functions that are solutions to our differential equation. The punchline, which is a great thing, says, look, all the solutions have this form. Some constant times the first function plus some constant times the second function, all the way up to some constant times the nth function. So this was called superposition. And so this was a nice idea. It says, look, when we have something that's linear and homogeneous, we can combine solutions very easily together. And we should also point out that this kind of expression here has a particular name. This is called a linear combination. In other words, we're combining things by addition and multiplying by constants. So that's a nice linear combination. Now, one thing we didn't talk about last time, but it's important to say, is a small fact. Because we say, look, if we have n solutions which are linearly independent, then yeah, all our solutions look like this. But the question comes up, are we guaranteed that we have a full set of linearly independent solutions? Because it's not so obvious. we know we can get solutions, but can we get enough of them? Are we guaranteed that we have a full set? Are we working with a full deck, you might say? So we want to actually make it explicitly clear that says, yes, we are guaranteed that this differential equation has, in fact, n linearly independent solutions. Okay, and we can actually show this. We have the tools. And indeed, we don't need anything more than what we have here to show it. Okay, so here we go. We're going to argue that we have n linearly independent solutions. Now, let's just do a special case. We'll do n equals 3. The same argument works for any choice of n. And so when we see n equals 3, we'll get the idea. We'll get the spirit of it. All right, so let's put this here to the side. So we have n equals 3. And so that means what? Well, we have y triple prime plus a sub 2x, y double prime plus a 1x, y prime plus a 0x, y equals 0. So that's our differential equation that we have. And now what we're going to do is we're going to use our fact that says, hey, if you tell me initial conditions, I have a solution. So what we'll do is we'll come up with some solutions that have some very nice initial conditions. So we'll have 3 solutions. We'll have y1, we'll have y2, and we'll have y3. And these are all of them solutions. So the only thing I need to do is tell you what the initial conditions are. So y1 at a will be 1, y1 prime at a will be 0, and y1 double prime at a will be 0. y2 will be slightly different. The function at a will be 0, but now the derivative at a will be 1, and the second derivative at a will be 0. And you can probably guess, okay, what's going to happen with y3? Well, 1, 0, 0, 0, 1, 0. Yeah, 0, 0, 1, exactly. So y3 of a, 0, y3 prime of a, 0, and y3 double prime of a, 1. There we go. All right, now the claim is these are linearly independent. All right, so if we can prove that, then we're done. All right, so how do we prove that? So, well, we have to recall, what does it mean to have 3 functions be linearly independent? Well, what it means is we look at combinations of them and say, how do we get 0 out? Now you might say, hey, let's use the Wronskian, but we're going to actually just go back to basic principles, which says, suppose that we let some constant y1 plus some constant y2 plus some constant y3 equals 0. And we want to show that all of our constants equal 0. And if we can do that, then that means that they must be linearly independent, because there's no redundancy. We need all of them. Okay, so let's see where to begin. So in other words, this is going to imply something. Well, let's take a look. We'll start by saying, hey, we don't know much, but we do know what happens at A. So we'll say, okay, plug in x equals A. And let's see what happens. Well, we'll get C1 times y1 at A plus C2 y2 at A plus C3 y3 at A. And that equals 0. Because this is true for any value of x, so it's definitely true for x equals A. Now, what do you see? Well, y1 of A equals 1, y2 of A equals 0, y3 of A equals 0. So we're going to get C1 times 1, C2 times 0, C3 times 0. So really, this becomes just C1 equals 0. Aha! We've made progress. So we've come to the conclusion that C1 equals 0. Now we're not done, but we're definitely started, because we need to show C1 equals 0, C2 equals 0, C3 equals 0. All right, well, what do we do next? Well, okay, let's think about what we have. Well, we've used the fact about the function at A, say, hey, there's something here about the derivative at A. Okay, so let's take our derivative, and then we'll plug in x equals A, and we'll see what happens. All right, let's do it. Let's do that. Let's see what we get. So we're going to get c1 y1 prime at A plus c2 y2 prime at A plus c3 y3 prime at A. And of course, that equals 0, right? Because when we take the derivative of the left-hand side, that's what we get. When we take the derivative of the right-hand side, that's what we get. All right, well, now we say, hey, y1 prime of A is 0. y3 prime of A is 0. y2 prime of A is 1. So this simplifies to C2. So wonderful. Now we know C2 is also 0. All right, 2 down, 1 to go. So how do we get that last one? Well, we've used what happens at the function at A. We use what happens with the derivative of the function at A. Say, hey, we haven't used the second derivative yet. All right, let's do it. So now let's take our second derivative, and then, as before, we'll plug in x equals A. Great. It seems like we can do this. So, okay. So we get c1 y1 double prime at A plus c2 y2 double prime at A plus c3 y3 double prime at A, and that equals 0. But of course, we know we get 0, 0, 1. So we have 0, 0. That's 1 times c3. So that equals c3. We say, aha. And that means that c3 also equals 0. And lo and behold, all our coefficients are 0. And so, yes, this is a true claim. These functions are linearly independent. And in some sense, they're very nice functions, right? Because now if you tell me any initial condition, you say, oh, suppose I want y1 at A to equal 5, and y2, okay, let's actually write this down. All right, so let's make up some initial conditions now. So these functions are really special. So suppose I wanted y at A to equal 5, y prime at A to equal minus 2, and y double prime at A to equal pi. Right? We can have weird numbers. Pi's not that weird, all things considered. Then actually, it's really easy if you have this specific set of solutions, y1, y2, y3, because what you can say is, oh, well, what you can say is, look, you're going to let y is 5, y1, minus 2, y2, plus pi, y3. Why? Well, because we have it set up so that at A, only the y1 contributes. We look at the derivative at A, only y2 contributes. We look at the second derivative of A, only y3 contributes. So if you were to find these three specific functions, then any initial value problem is super, super easy to solve. Now the good news is we don't actually need these three specific functions, which is great, because in general it's kind of hard to find these three. The punchline is we just need 3 of them which are linearly independent. And there's actually going to be lots of different options on how we choose to pick them. Generally, the rule of thumb is you pick the 3 that are easiest to find. Or if we're doing nth order, you pick the n that are easiest to find. Okay, so now we know that if we have a nice differential equation, we can find linearly independent solutions. Okay, good. Well, the only problem now is to actually find them. We'll get to that. But first, we did some theory ideas. Let's take a nice relaxing break and do a little bit of practice. Okay, so here we go. Show that x log x, and x squared, so we have 3 functions, are linearly independent solutions of x cubed y triple prime minus x squared y double prime plus 2xy prime minus 2y equals 0. And then also find the particular solution satisfying y1 equals 3, y1 prime equals 2, and y double prime of 1 equals 1. Okay, let's go back to the first sentence. And there's actually 2 important things that have to be done, which which means we have double the work that we normally do. Because normally it's like one sentence, one thing to show. Because it says, show that they're linearly independent solutions. So there's two ideas here. One thing is we have to say, look, we have to show that they're linearly independent. All right, that's one thing we have to show. And the other thing we have to show is, oh, and these are solutions. So we have to do two things here. Let's start with linear independence. And let's use the tool we talked about last time. You might recall that we learned something called the Wronskian. And the Wronskian is this wonderful, hey, I can help you check if something's linearly independent or not. I have the technology. So let's do that. So here we go. We're going to take the Wronskian of these three functions. X, x log x, x squared. Now, you might be wondering, does it matter which order you choose to put them into the Wronskian? And the answer is no, it doesn't. The end result will be the same up to a plus minus. And we only care about are you 0 or non-zero, so changing it by a plus or minus doesn't change are you 0 or non-zero. Okay, so how does the Wronskian work? It involves taking a determinant. So you're going to make a little matrix. And the way you make the matrix is you say, okay, the functions fill the first row. So it's a matrix of functions x, x log x, and x squared. And then what happens is to keep going down the rows, you keep taking derivatives. And we need to make enough rows so we have the same number of rows as we have columns. In this case, we have 3 columns, so we're going to take derivatives twice, right? So that we get 3 rows. So the derivative of x, 1. Derivative of x, natural log of x, well, we can do a product rule. So we say, okay, well, if we take the derivative of x, it's 1, and then keep the log x alone. So that's log of x. Then we have x times the derivative of log x, which is 1 over x. X times 1 over x is 1. So the derivative is log x plus 1. And the derivative of x squared, 2x. Okay, now next row, take derivatives again. 0, derivative of log x plus 1, 1 over x, and the derivative of 2x is 2. All right, now we need to take this determinant. So the way I like to do determinants is just diagonals. Now this works for 2 by 2 and it works for 3 by 3. And the good news is, in practice, that's usually all we have to get to. So now let's do it. So diagonals, I would go down, so I have x times log x plus 1 times 2. Okay, so that would be 2x times log x plus 1. And then the next diagonal, I have x log x times 2x, whoop, hit the side, wrap around, times 0. Aha, times 0, 0. Yes, 0, our friend. We love zeros in matrices when it comes to taking determinants because it makes a lot of things 0. Okay, x squared times 1 over x. All right, well, x squared times 1 over x is x. Hey, that's not so bad. Good. Now, we're only halfway done. We took the diagonals going downhill. Now we need to take our diagonals going uphill. And here's the thing to remember about determinants. When we look at diagonals going down, add. Diagonals going up, subtract. So, when we look at 0 times log of x plus 1 times x squared, well, 0, of course, makes the whole thing 0. But we're going uphill, so we subtract 0. All right, good. And notice we have a plus 0 and a subtract 0, so the zeros cancel, right? Well, they would be 0 anyways. Okay, 1 over x times 2x times x. Well, that contributes the total of 2x, but remember we subtract, so minus 2x. And then we have a 2 times 1 times x log x. Okay, so when we multiply that together, that would be 2 times x log x, but again, remember to subtract. So you have minus 2x log x. So this is 2x log x, so multiplying that 2x through, plus 2x plus x. minus 2x minus 2x log x. And we say, wow, this is nice. We see cancellation happening. And for example, the 2x log x cancels, the 2x's cancel, and we're left with x. And what's nice about x? Well, this is not the zero function. So remember, we're asking, is this 0 or not 0? When it comes to the Wronskian, we're talking about functions. You say, hey, it's not the 0 function. And so we know that they're linearly independent. Now, skeptics in the audience might be saying, hold on a second, Steve. Wait. What about x equals 0? You're right. There is something strange about x equals 0. And you might be saying, okay, why? Why should we not worry about the fact that there might be a place where the Wronskian equals 0? But in fact, let's look closely here. Look at this differential equation. What do you notice? You might say, well, it looks like a differential equation, Steve. Okay, let's come back to what we had just a few minutes ago and compare this differential equation with that differential equation. What do you notice? Here, you see that? That means that the leading coefficient is 1. Here, the leading coefficient is x cubed. Oh, okay. So what does that have to do with anything? Well, what happens here is say, suppose we make this a 1 in the front. Then we can do that. We have technology called divide by x cubed. So we say, hey, this could be thought of as a differential equation. Y triple prime minus 1 over x, y double prime plus 2 over x squared, y prime minus 2 over x cubed, y equals 0. And now we say, look, in this form, we can talk about solutions. And we know that solutions exist as long as the coefficients are continuous. Where is the coefficient? It doesn't really matter which one you pick. Where is it not continuous? At 0. Yeah. So this breaks at x equals 0, which means we can't make any conclusion about what's happening at 0. So even though, yes, it is true that we get 0 out of the Wronskian at a particular value of x, that's a place where it's going to break down. So it's okay that we got a particular place where we had 0. No problem. All right, good. So we've now done 1/3 of the problem. We've shown we have a set of linearly independent functions. We haven't shown that they're linearly independent solutions. So that's where we'll go next. All right, so here we go. Off to showing that there are solutions. So we have 3 functions. We have to check each one. So let's start by checking in with our function x. And so what does that mean? Well, we're going to plug x into here and see what we get. So we're going to take x cubed times the third derivative of x minus x squared times the second derivative of x plus 2x times the first derivative of x minus 2 times just x. Well, the third derivative of x is 0. The second derivative of x is 0. It's very easy to take derivatives of x. The first derivative of x is 1. So what we have is we have 2x times 1 minus 2x from here, and that equals 0, which means, yes, they are indeed, well, I should say, this is indeed, x is a solution. All right, 1 function down, 2 to go. So next one, x log x. Okay, so here we go, x log x. Well, that'll be x cubed times the third derivative of x log x minus x squared times the second derivative of x log x plus 2x times the derivative of x log x minus 2 times x log x. All right, now, can you do the third derivative of x log x? You can actually. In fact, you can almost do it in your head right now. In that we have a little bit of a cheat. You remember the Wronskian here? The way we built this was by derivative. So we have function, first derivative, second derivative. So the third derivative would be if we took one more derivative. Okay, so it really means what's the derivative of 1 over x? Now, if you're thinking about it, that's x to the negative 1 power. And the way you take that derivative is that negative 1 comes down in the front. So we have negative 1 x to the negative 2, minus 1, minus 1. So this would be x cubed times minus 1 over x squared. Then minus x squared. Well, second derivative, we can refer back here. That's 1 over x. Plus 2x, first derivative, log x plus 1. And then just the function, 2x log x. Okay, so that would be here. We have x cubed, 1 over x squared. And so that's minus x. Here, another minus x. Now multiply out, plus 2x log x plus 2x minus 2x log x. And if we've lived a good, clean algebra life, things should happen. Well, 2x log x is canceled. And then we have a plus 2x, a minus x, and a minus x, so they all cancel. We've done it. We've lived that good, clean algebra life, and we get 0. So yes, x log x is a solution. Whew, that was probably the tough one. Okay, well, that leaves us with x squared. So we're going to take x cubed times the third derivative of x squared minus x squared times the second derivative of x squared plus 2x times the first derivative of x squared minus 2 times x squared. Well, again, we can use our cheat sheet here. So the next derivative, the third derivative of x squared will be 0, right? Because we take 2, derivative of 2 will be 0. So we have x cubed times 0 minus x squared times 2 plus 2x times 2x, and then minus 2 times x squared. Well, that'll be minus 2x squared plus 4x squared minus 2x squared. And we have minus 2 plus 4 minus 2. Ah, yes, again, 0. Well, of course, we should have expected it. Actually, because we know we're checking solutions, we would say, look, if we didn't get 0 here, one of two things happened. Either they lied to us and they gave us something which wasn't a solution. Well, let's give them the benefit of the doubt. They made a mistake. You know, mathematicians, they're human too. Or, which is probably more likely, we made a mistake in some of our algebra or maybe taking a derivative, which means, hey, let's go back and check our work because our goal, we want to get all the points. It's a good goal. It's a wonderful goal to have. Okay, so we've successfully finished sentence 1. We now know that we have solutions and a full set of linearly independent solutions, which is fantastic. We're ready to go on to the second part of this problem. And what's the second part? It says, well, we want to find the particular solution which satisfies something. Well, looking at our differential equation, we see it's a linear differential equation and it's homogeneous, which says that solutions look like combinations of 3 linearly independent solutions. Well, we have 3 linearly independent solutions. So that says, hey, we have to look like something times x plus something times x log x plus something times x squared. Every solution has that form. Okay, great. So it's down to saying what are A, B, and C. Well, to do that, we're going to be using our initial conditions. And initial conditions involve y prime and y double prime. So let's take a second and find y prime and y double prime. And this is a case where, hey, we have the derivatives and we have the second derivatives. So we can make it not too hard on ourselves. Okay, it's a times 1 plus b log x plus 1 plus c times 2x. And then y double prime, well, we get a times 0, so that just goes away. B times 1 over x, and c times 2. All right, there we go. There's our 3 derivatives. And now what we can do is we can plug in x equals 1 because, whoops, plug in x equals 1 because that's where our initial conditions are at. So we'll have a times 1, b times 1 times log of 1. Log of 1 is 0, so that says 0b. So plus c times 1 squared has to equal 3. Here we'll get a. Log of 1 plus 1, 0 plus 1 is 1, so we'll get plus b. And then c times 2 times 1, which is 2c, and that equals 2. Finally, there's nothing with a. B times 1 over 1, which is b, and then plus 2c, and that equals 1. All right, so now we have our bread and butter. This is the kind of thing that we're going to do a lot of, so we should get comfortable at doing this. Namely, we have 3 equations, 3 unknowns. So, well, we want to figure it out. And these are nice equations. We call this a linear set of equations. And we start saying, okay, can we solve? Now, the punchline is when they're linearly independent solutions, we're guaranteed we can solve. There's no problem, other than actually figuring out how to do it. So there's lots of things we can do, but oftentimes you can sort of look at it and come up with some strategies. So when we look at this, for instance, we say, hey, look at this b plus 2c. That looks an awful lot like b plus 2c right above it. So we can do some substitution. We say, hey, look, this a plus b plus 2c, that really can simplify. And what does it simplify to? It really becomes a plus 1, right? Because b plus 2c is 1 equals 2. And now we say, look, that tells us a equals 1. And now we've got some steam. We're going here. We say, well, wait a second. Look at this first equation. It just involves 1 and c. So that says 1 plus c has to equal 3. All right. Well, that says c better equal 2. Like, wow, 2 down, 1 to go. Well, how do we finish? Well, just pick an equation. How about this last equation here? That would say b plus 2 times c, so that's 2 times 2 makes 4, has to equal 1. Okay, so that says b should be negative 3. And we did it. We found a, b, and c. Now, to finish it up, those are the coefficients, and we want the solution. So the solution is a function. So our answer would be y equals a times x, so that's going to be x. B times x log x, so b is minus 3, so that's minus 3x log x. And c times x squared, so plus 2x squared. And we're done. We did it. We found our particular solution. Wow, that's great. We were able to do our problem, and there's lots of parts here. This problem definitely has lots of parts. But when you look at any single part, nothing is too bad. It's just a matter of just being careful with the computations, being consistent, and we get to the answer. Good times, good times. All right, well, let's get back to our discussion. Okay, so how do we actually go about solving one of these types of problems? So what do we mean by one of these types of problems? So we want an initial value problem of something which is homogeneous, so that means something equals 0, and it's linear. Well, it turns out there's basically 2 big steps. Now, what are the steps? Well, the first step is 1, find n linearly independent solutions. So in other words, you're looking for your y1, y2, so forth and so on, up to yn. The second step says, okay, now that you've found your solutions, we now apply the principle of superposition and say, hey, we know that all our solutions look like some constants times the functions added together. And so we just have to figure out what are the constants to satisfy the initial conditions. So 2 steps, it's a very big simplification. What do we think about them? Well, here, this step, it's very mechanical in some sense, because we understand, like, we have our functions. We understand, okay, we're going to combine them together in various ways, and it leads us to a system of equations. But these can be solved. We have tools to solve it. There's lots of tools to solve systems of equations when they're linear systems. We have things like substitution, cancellation, linear combinations of functions to eliminate variables, and so forth and so on. The first part is the hard part. And so I'm going to write hard because it's not obvious how to go about finding these solutions. I mean, how does one make sure that we find linearly independent solutions? Because if you write down a random differential equation, you're going to run into troubles. So that's going to be the one that's going to be the most challenging. So we're going to spend most of our time when we're talking about solving differential equations is how to go about finding these solutions. Now it turns out that there's a nice case. So there's one really special case where it says, hey, there's actually a nice way to find the solutions. And that's what we're going to spend some time on. And so what's that special case? Well, we're going to add something. So we don't just want it to have an initial value problem that's homogeneous and linear. We're going to say one more thing. What's that one thing that really puts it over the top? And that is if it's constant coefficients. Then we say that's a beautiful differential equation. Now, if you're thinking about, okay, what does it mean to have constant coefficients? Well, it just means that the functions in front are no longer functions of x, really. They're just numbers. So these are like, could be like 5, 7, 2, negative 17, all sorts of numbers. Any number you want, but it's a fixed value. And so we will show that actually we can always find n in the linearly independent solutions. We'll talk about how we do it. And where does it begin? Well, we say, we have essentially constants showing up in the front. So we say, well, is there some function where when we look at the derivative, it looks a lot like the function? In other words, where the derivative doesn't change it much. And the answer is, yeah, we have one of those. In fact, it's one of our favorite functions to talk about. It's this function y equals e to the rx. We love the exponential function. We said that before in our class. It says, we love the exponential function. And we love it just because of how little it changes. And so let's actually take a look at the exponential function and say, hey, look at this. Isn't this beautiful? In particular, if we look at, say, the derivative of e to the rx, what happens there? Well, what happens is the r comes down, e to the rx. And this is the chain rule. So you really should think of it as the derivative of the outside is the exponential function. Leave the inside alone, times by the derivative of the inside. All right, how about the second derivative of e to the rx? Well, what will happen is it's like you're taking the derivative of the first derivative, and another r comes down. So you have r squared. R squared e to the rx. Okay, what about the third derivative of e to the rx? And you might say, look, Steve, I know how to play this game. R cubed e to the rx. And so forth and so on. And what if I ask you for just some derivative, say the kth derivative of e to the rx? So we've taken k derivatives. What should we have? Well, we'll have r to the k, e to the rx. And so what's happening is we say, if we plug in this function e to the rx, and for y, the same as we did for like, hey, how do you verify a solution? Well, we'll get we have an e to the rx there, an r times e to the rx, so forth and so on. Here you'll have r to the n minus 1, e to the rx. Here you'll have r to the n, e to the rx. And you say, oh, all the pieces have e to the rx. So you say, all right, pull it out. So you have e to the rx, and then you have everything else. So this is, again, applying this rule and for our derivatives. So what do we have? Well, what we have, and this is our great, hey, check this out. this is a polynomial in the variable r. And sometimes I think it might be called the character polynomial. But the punchline here is, look, we want this to equal 0 because we want a solution. So how can something equal 0? Well, e to the rx, this piece over here, is never 0. That's one of the important things about exponential functions. Exponential functions are never, ever 0. All right? So we know that can't be 0, which means that we want this polynomial to be 0. Well, that means we need to look at the roots of the polynomial. So if you find a root of the polynomial, in other words, some value for r that makes this whole thing 0, then we say, oh, that root gives us solution. Because we say plug in e to that root x. And so we say, so we've somehow reduced the problem to say, look, if I want to solve this differential equation here, it's all about finding the roots of a polynomial. So we've gone from a differential equation problem and turned it into an algebra problem. Algebra, we know that. We've seen it before. And so we have some tools. We have the technology. All right, so again, the punchline, we want to focus on these roots because roots give solutions. And that's the important thing. Now, the other thing we should point out really quickly is if we have a differential equation in this form, we can just jump straight to this polynomial because we say, look, the degree of the derivative is r to the power. Now, you might say, well, hey, what about this one? Well, there's no derivative of that. We can think of that as the 0th derivative, which means r to the 0, so that would become 1. So, as a quick example, we can just make up a differential equation. Suppose you have y to the 5th minus 4y to the 3rd plus 7y double prime minus 2y equals 0. Now, this is a 5th order differential equation. And what would it lead to? Well, we say, look, fifth derivative leads to 5th power, r to the 5th. Third derivative, 3rd power, r cubed. Don't forget the minus 4. 7, r squared. Minus 2, r to the 0, which is 1. And then we say, look, instead of trying to solve this differential equation, we really just have to solve this polynomial. Now, solving polynomials sounds easy, but I will say it's known. In fact, there's a wonderful result in mathematics that says solving polynomials can actually be hard. And you might know that there's a quadratic formula. We'll talk about that in a second. That solves quadratics. There is a formula to solve cubics. If this is the quadratic, the cubic is probably about this long. I think if we could fit it all on a screen. There's also a formula that solves 4th order, would fill up the monitor, wherever that is. It would take up the whole space. And when you get to the 5th order polynomial, so those are called quintics, there's no formula. It doesn't exist. Not that we haven't found it, but it's mathematically known. There is no formula that solves all quintics. So in practice, it can be hard. So if somebody just hands you a random polynomial, you're not going to be able to make a lot of practice. Now, in principle, it can be done. So there's a wonderful result. In fact, it's fundamental. So we can call it the fundamental theorem of algebra. And it says, if you have a polynomial of, like a 5th degree polynomial, there's 5 roots, counting possibly repetition. And so the fundamental theorem of algebra says, all nth degree polynomials have n roots. So we know that they do exist, and sometimes we might just have to be satisfied with numerical approximations, and there are ways to get numerical approximations to roots. And so our goal has turned into algebra for now. And there's going to be some discussion, like, okay, how do we handle different roots? How do we handle the same roots? In other words, repeated roots. How do we handle complex roots and things like that? But for now, at least we are like, hey, we can make progress on these types of nice differential equations. All right, so let's try a little bit of practice. Okay, so here we go. Now, first thing, there's a little fact we're going to state, but we're not going to prove it because we don't quite have all the technology that we need to prove it. And it says the following. Suppose you have some numbers. So you have R1 up through Rk, and they're distinct numbers. So in other words, they're different. They're all different numbers. So it could be like 17, 2, 4, negative 10, and so forth and so on. And so, okay, so we have distinct numbers. Then if we look at the functions, so e to the r1x, e to the r2x, so forth and so on, these functions are linearly independent. So distinct numbers says, hey, all these functions are different from each other. In essence, it says, look, these functions are growing at different rates because the coefficients r1, r2, rk are somehow telling you how the exponential functions behave. And so the larger the value for r1, it says, look, it blows up faster. So if I have a small value for r1, it'll blow up, but slower. Or if a negative value, it will actually go down. And so somehow the saying they have different rates of increase says, hey, they're actually different functions. Now, let's do an example. Find the general form for solutions of this. Here we have a second order differential equation, but we have boxes, which means we need to fill a number. So we have our nice random generator here. And so we're going to just be mixing our cards up, around, come on, randomness. We're counting on you. Okay, now, all right, that's somewhat random. I have no idea what cards are coming up. And hopefully we don't get a queen, because I don't know how to do an equation when we don't have numbers. Ah, good. We have just numbers. One of these days, we're going to have like a king or a jack or a queen show up, and we're like, how do we handle that? Well, get another card. All right. So we're going to have 9 y double prime plus 6 y prime minus 5y equals 0. All right. There we go. Now, we say, okay, great. Can we factor it? Maybe. I don't see it. Now, it doesn't mean that it's not factorable. It just means I don't see it. And so, but that's okay. Even if we can't factor it, we're sorry. Now, you might say, Steve, factoring, that's the differential equation. You're right. I should have pointed out that we've omitted a step here. It says, all right, if we want to solve this differential equation, we're thinking about e to the rx. So we're thinking about solutions have the form of y equals e to the rx, and then this becomes 9r squared plus 6r minus 5 equals 0. All right. So that's what I mean by factoring. This doesn't factor. Well, the good news is even if it doesn't factor, we can still make progress because I said we have that quadratic formula. So it's good to remind ourselves the quadratic formula. So that says what? If you have ax squared plus bx plus c equals 0, then x equals negative b plus or minus the square root b squared minus 4ac, all that over 2a. All right, so there's our quadratic formula. And we say, okay, so let's apply it here, a, b, c. So what do we get? Well, we get r is equal to negative b minus 6 plus or minus the square root b squared, 36, minus 4 times 9 times negative 5. Well, 4 and 5 multiplied to 20, and then 20 times 9 is 180. So that's going to be a plus 180. Now, y plus, well, minus here, minus there, 2 minuses become plus. And that's going to be divided by, downstairs, 2a makes 18. All right. Well, as they say, Now, we can actually make a quick observation before we go too much further. Let's look at what's inside the square root. So we have 36 here. Notice that 180 is actually a multiple of 36. I don't know if we can spot that quickly, but we can spot it slowly, right? So if you take 36 times 5, you'll get to 180. Because actually, at 9 times 4, 9 times 4 is 36. And so we say, oh, so this is really 36 times 1 plus 5, which really means this is 36 is 6 times 6 times 6. So 3 6s. Well, wow, what a coincidence. Now, if we were taking the cubed root, we'd be like, wow, that's amazing. We're taking the square root, so like, oh, that's ordinary. So what does this become? Well, it becomes negative 6 plus or minus. So since we're taking the square root, we can put 2 of them and pull it out. 6 times the square root of 6 all over 18. Well, okay, 6 we can pull out and divide into 18. So we can write this as negative 1 plus or minus square root of 6 over 3. All right, so there we have it. There are our 2 roots. Now, remember, the solutions have the form y equals e to the rx. And we have r, and we have 2 of them. They're distinct from each other. So we say, okay, that says we have 2 solutions, namely e to the minus 1 plus root 6 over 3, because that's one of our choices for r, and multiply that by x. And then we have e to the minus 1 minus root 6 over 3, and we multiply that by x. All right, great. Now, so those are 2 solutions. And what are we looking for? Well, we're looking for something called the general form. And I realize now, whoops, I forgot to tell you what the general form is. And so let me actually tell you what the general form is. So when we talk about the general form, we've actually written it down, we just haven't given it a name. That means you have your constant y1 plus constant 2, y2, and so forth and so on, all the way up to constant n, yn. In other words, it's that linear combination of your solutions. So here we have 2 solutions. We know they're linearly independent if we believe our fact, and the fact is true. I won't lie to you, I promise you. So to get the general form, we say, okay, we just need to multiply these by constants. You can use C1, C2. Of course, we use this notation here when we say, well, we don't know how many there are, but oftentimes it's easier when we say, oh, there's only 2 or 3. We'll just use a couple letters of the alphabet. So say A times the first plus B times the second, and there we have our nice general form. And that's it. That's our solution. So, woohoo! Great! We did it. We can solve something, right? We solved the second order. Oh, wow, this feels good. I think this might be our first real honest second order differential equation that we've solved. We've solved some other ones where we said, oh, we can kind of guess the solution, or like, oh, it's like, oh, this is really a first order in disguise. But this one is like, wow, we can solve it. So life is good. Okay, one last idea and one more example to help us see it. So here we go. Last thing for this session. And there's a fact. And we'll come back to this fact, but we'll say it right now. It says, suppose you have a value r. Now, r here represents just an arbitrary number, any number you like. So it doesn't have to be a whole number. And k is a whole number. So I have r, very arbitrary number. I have k, whole number. Then look at these functions. So they all have e to the rx in it, but the difference is what's in front. So here there's a 1, here there's an x. And so the idea is you basically have different powers of x in front. And the punchline says those functions are linearly independent. Now, it's not too hard to show this. It really follows from the fact that if you look at 1x all the way up to x to the k minus 1, these functions are linearly independent. And probably the easiest way to do that is if you trust the Wronskian, and you should. The Wronskian is a true function. It's very simple to take the determinant of the Wronskian in this case. All right, but for now, we'll just accept that as a fact. And wonder why this fact is mentioned on this page when the only thing else on this page is an example. Okay, well, let's start with the example. It's very similar to the previous problem, where it says find the general form for solutions. But now, in the previous problem, they were like, just give us any numbers. And now they're like, no. We're after a very particular thing. So something probably happens in this differential equation that, needed to be just right. So they wanted to make sure it's like, hey, we want to make sure we have something that works just the right way for us. Okay, so where to begin? Well, we do the same thing that we had before. We say the solutions look like y equals e to the rx, and we say this, differential equation becomes a polynomial. In particular, becomes a polynomial 4r squared minus 12r plus 9 equals 0. Okay, all right, great. Well, what's going on? Well, why this polynomial? What's so special about this? Well, of course, we want to try to find the roots. Now, you have some options. You can do factoring if you can, because probably if they hand you something, there's probably some way to factor it. As a general rule of thumb, if you're handed a differential equation with at least constant coefficients, it probably factors nicely because it was designed to be able to be solved. If you can't, well, it's a quadratic, so you can still use the quadratic formula. Now, this one does factor nicely. I know because I actually have done this problem before, but we'll check, right? So how does it factor? Well, it factors as 2r minus 3 and 2r minus 3. And you can check this. 2r times 2r is 4r squared. Then 2r times minus 3. And minus 3 times 2r, well, that's minus 6r, that's minus 12r. And minus 3 times minus 3 is 9. All right. So yes, good. Now, what do you see? Well, we say, aha, we have our roots are 3 halves and 3 halves. And now this one, we're like, hey, we found our roots. And we know that our solutions are like e to the root times x. And so we're like, great, we'll write down our answer and we'll be done. Y equals some a e to the 3 halves x plus some b e to the 3 halves x. And we're like, woohoo, we did it. Look how quick that was. And we'll pat ourselves on the back, and then somehow we'll feel a sense of dread. Wait a second. That almost seemed too easy. Uh-oh. Let's think about it. Have we solved it? Did we succeed? Take a look. What do we have? We have these two functions, e to the 3 halves x, e to the 3 halves x. So I said, look, here's a solution, e to the 3 halves x. Here's another solution, e to the 3 halves x. Have I gained anything if I told you the same function? The answer is no. I haven't gotten anything fundamentally new. These aren't different from each other. They're the same function, which means really this is not two different solutions, because we could have combined them together, and this says, oh, this is really like a plus b e to the 3 halves x, and then this is just a single constant, which says, oh, whoops, we still only have one solution. Darn it! Ah! So now we're in trouble. All right. So how do we get our second solution? And you might say, well, okay, maybe there's some other value for r that works. And the answer is no. We already know if it has y equals e to the rx, the only r that can work is 3 halves. So there's no other, maybe r equals 2 or r equals 5 halves, r equals negative 3. None of those other values for r will work. Because the only way r can work is if it solves that differential equation. Solves that polynomial. All right. So now we're kind of like, What do we do? What do we do? All right. So at this point, you're probably thinking, maybe it has something to do with the fact. Yeah, it does. But let's suppose we didn't have that fact written right in front of us, sort of like, hey, look at me. So what can we do? Now, one idea, and this shows up a foreshadow of things to come, that says, e to the 3/2 x is close. Why don't we just try to modify it a little bit? And we say, okay, well, how to modify it? And that's actually, a good, valid question to ask. And so what we can do is you can say, well, let's think of, instead of just saying, e to something x, we'll say, look, we like the e to the 3/2 x, so we'll just put a little function in front, u of x. And we'll try to understand what happens and say, look, what's a good u of x? How do we pick u of x? So if we can figure out how to pick our u of x so that it still works with this differential equation, then we're winning. Okay, so we say, okay, let's think about if we're going to go into our differential equation, we need y, we need y prime, we need y double prime. So we plug in y prime, let's compute that. Well, okay, we can leave the first alone, get rid of the second. That would be 3/2 u of x, e to the 3/2 x, plus, okay, get rid of the first, u prime of x, times the second, e to the 3/2 x. If we look at y double prime, okay, well, okay, again, leave the first alone, get rid of the second, so that would give us 9/4 u of x, e to the 3/2 x. And now the next term, okay, we leave the second alone, take rid of the first, so we'd have 3/2 u prime, e to the 3/2 x. But notice here, if we leave this alone, we'd also have 3/2 u prime. Oh, why is that x so low? You need to go higher, x. There we go. So we'll have a 3/2 u prime, e to the 3/2 x coming from both places. So really, if we put them together, we'll get a 3 u prime of x, e to the 3/2 x. So there's really two derivatives showing up combined to get that term. And then, of course, take rid of this, and we'd have u double prime of x, e to the 3/2 x. Okay, so we have y prime, y double prime. All right, now what do we want? Well, we want to take 4 of the y double primes. We want to take minus 12 of the y primes, and we want to take 9 of the y's, right? 4y double prime minus 12y prime plus 9y. So we're going to add these up. So we'd have, over here, we'd have 4y double prime minus 12y prime plus 9y equals, and now let's go through. So the u of x, e to the 3/2 x, well, we'd have 9, 12 times 3/2. Well, that becomes 18. It's being subtracted. 4 times 9/4 is 9 being added. So it's 9 minus 18 plus 9, which makes 0. Okay, so those would cancel. Okay, now let's go to the next term. We'd have minus 12 here. 4 times 3 makes plus 12. So when we put them together, they cancel. And here, for the u double prime, well, it's just one of them. So we end up with 4 u double prime of x, e to the 3/2 x. Now, what do we want? Well, in order to be a solution, we need this has to equal 0. Now, we look at them and say, well, there's 3 pieces here. There's the 4, there's the u double prime of x, there's e to the 3/2 x. We say, well, look, the 4, that can't be 0 because it's 4. E to the 3/2 x, well, an exponential function can never be 0 because that's one of the nice properties of exponential functions. So I say, oh, okay, so a good u of x has the property that u double prime of x equals 0. Okay, so now we start thinking, well, what functions have it when we take the second derivative, we get 0. 1 has that. Anything else? X has it as well. So if you wanted to, you could even just integrate this twice, right? If you integrate it once, you'll get a constant. Integrate it a second time, you'll get a constant times x plus a new constant. So we say, oh, that says u of x has the form of ax plus b. And now we come to our conclusion that says, hey, remember, what did we say? Well, we said, look, we wanted a solution that looks like u of x times e to the 3 halves x. So we say a nice set of solutions have the form ax plus b e to the 3 halves x, or if you like, that's ax e to the 3 halves x plus b e to the 3 halves x. And notice we have two variables, a and b. I call them variables, I should call them constants, but they're choices that we make, arbitrary choices of these two functions. And if you look, you say, oh, wait a second, well, hey, that's like e to the 3 halves x, x e to the 3 halves x. These are linearly independent. And they're both solutions, because that's what this computation shows. So we said, oh, I just need to add an x there. And then that works. So, thank goodness I had that space there. Well, it's almost like I planned for there to be a space. Now, what's the general principle here? So there's a nice sort of general principle. We'll put a comment here. And we'll say this again in our next session. So our general principle says if we have repeated roots, then what we'll do, use powers of x. And so in particular, suppose you have r, and this is done k times. Well, I shouldn't call it r because r is my variable. Okay, well, let's just say these are our roots are r k times. Then what you would have is you'd have the functions e to the rx, x e to the rx. So you just start with e to the rx, and you keep multiplying by x until you get up to xk minus 1 e to the rx, so that you have k of these. So there's k of those functions as well. So if we have repeated roots, root repeated k times, we say, look, we like that e to the rx. We just got to keep bumping it up enough times so that we have enough solutions. All right, so that's good. So we've talked about distinct roots. We talked about repeated roots a little bit. The things are going to get next time a little complex. And then we'll put it all together and say, here's the principle. And so then we'll be like, yes, now we can solve. We can solve just about anything. Woohoo! Well, as long as we have constant coefficients, linear, homogeneous. But, you start somewhere, and it's a great place for us to start. But for now, it's also a great place for us to stop. All right. See you next time.